We now start part 6.3, power loss in transformers. In 6.2, and in fact, in all the calculation questions, we generally deal with ideal transformers where there's no loss in power. But that's not true, right? In effect, right, most transformers do lose power. In reality, we know that things are not perfect, right? So you have experienced this before, right? In fact, if you have touched your power brick for your laptop or your handphone charger after using it for some time, you realize that it's hot, right? That's because there's power loss in transformers, right? And the efficiency of the transformer is the power output from the secondary coil over the power input to the primary coil. So in this part, we are concerned about how these energies can be lost, right? So it can be lost in these four ways, and I'll talk about each of them one by one. Firstly, heating due to eddy currents. 2, resistive heating in the coils. 3, heating due to hysteresis. I'll talk about that in a bit more. And number 4, leakage of magnetic flux. The slightly harder concepts to grasp here are 1 and 3. So first, heating of the soft ion core due to eddy currents. We have learned in electromagnetic induction that in Lenz's law that the induced current, right, will oppose the change, right? And Faraday's law says as long as there's a changing magnetic flux, there will be an EMF induced and hence current induced if it's a closed circuit. And that's what we have here, right? Here the current is going clockwise, right, which is creating a B field upwards. This increase in let's say this current is increasing. This increase in B field therefore induces a current using Faraday's law and Lenz's law in the in the clockwise direction. In the clockwise direction to counter this B. Let me say again. This current is coming in and it's creating a B field up. Imagine that this current is increasing. Right? Imagine this, which means the B field strength is getting stronger and stronger, pointing upwards. By Faraday's law and Lenz's law, induced current must then be created to counter this change in B field. So B field is increasing. If you use your right hand grip rule, you try to create a clockwise current to counter this increase in B field. Okay. And if you look at this core, it's rather big. So it allows a hard, right? It means that the resistance is rather big, means that resistance is small. It means that the induced current is large, right? So this current we also call eddy currents. And at this point, I recall that many students ask me, how is eddy currents different from induced currents? Well, eddy currents are induced currents, but in these cases of power loss, we use the word eddy simply because we want to show that it is the currents that causes energy to be lost, right? So it's like eddy currents. It's also used in words like eddy vortices when a car travels, right? So this word eddy refers very specifically to currents that causes energy to be lost. So an induced current that is losing, that causes energy to be lost is called an eddy current, if I may phrase it that way. Okay, so if you want to prevent energy loss, right, what you need to do is to slice up the core in the following manner. You have one layer of metal and you have one thin layer of black, which denoted by this black line, one thin layer of laminate, right? That means something that does not conduct electricity. And then repeat this structure. How does this limit current flow? Previously, you had a big block of metal, right? And current can flow through them quite easily, right? But now if you laminate it, your currents are now smaller in nature because of the resistance, right? Due to the lamination, right? So if you have reduced the current using P equals I squared R, you reduce the eddy current using P equals I squared R, the power loss will also be reduced. Okay. Next, let's talk about resistive heating in coils. Right, in the primary and secondary coils of the transformer, they are made of wires. And if they're made of wires like copper, they have resistance. So we'll send a current through them, there is power loss, right? So part 2 is pretty straightforward, right? The wires in the transformer have resistance and hence you lead to resistive heating. Part 3 is a little bit more interesting, hysteresis. I need to introduce to you an idea of hysteresis. The soft iron core are made out of things like domains, right? So you have learned this in secondary school, I hope. And so when you send a certain magnetic flux through them, it retains a bit of the magnetization. But if the magnet is pointing up and later on you make the BU point down, the soft iron core has to orientate its magnetization to go down. This constant rotation of the magnetic poles, right, is actually due to the orientation of the spin of electron. Okay, so when you keep switching the direction of magnetization in the soft iron core, right, you will need to spend energy to switch it around. Okay, and that energy is lost as heat within the core. If I give an analogy, if you go to MRT that's packed and you were to keep rotating yourself to face front and back every other second, there will be a lot of friction, right? And there will be a lot of heat produced. And of course, anger, right? With your fellow passengers. I do not recommend that you do this, right? So that's just an example that I state. Okay, so that's how hysteresis works. It works like that. Okay, hard materials are not used for the core because they strongly retain their magnetization after the field is removed. So even more energy is required to reverse this magnetization, right? So soft iron cores are used because number one, they can change the magnetic directions more easily compared to hard magnets. Okay. So these are the domains, right? When you align and disalign them, energy is required. Okay. Next is flux leakage, right? If you look at the transformer, right, and you send, let's say you have a coil over here, right? Coil over here. You will create a flux like this, right? We generally assume that the flux stays within the donut. But that's not always true, right? Because in reality, there's some chances of this happening. This flux is fine. This flux is fine. But you can have some flux that goes like this. The flux leaks beyond the donut, which means that on the left hand side you have 4 arrows passing through, but on the right hand side of the secondary coil you only detect 3. So this leakage of flux causes energy to be lost because you orientate the BFU, but the BFU is not detected by the other side. So some energy is lost, which causes the transformer to be less than efficient. Okay, with this I've come to the end of the whole chapter, right? And I provided you a summary on page 22 of your notes, right? And these are the 6 key points. 1, diode allows current to flow in one direction. Rectification is a process of converting AC to DC. I also rewrote for you the definition. Please read it again. And also given you a very helpful table to look at the root mean square values for a sinusoidal AC and a half wave rectified sinusoidal AC. I also mentioned ideal transformers, right? 100% of the power is transferred told you how the four ways in which energy can be lost, right? You need to know a bit more details other than the names. And lastly, I've given you this equation, right, for ideal transformers. With that, I come to the end. Thank you very much.